After those reactions, draw your section, 4-meter section, put in what you know, 6.5454, and then put it in equilibrium, right? That's basically all there is to it. The shear diagram needs to oppose whatever's going on out here to the left side. So the shear force, that's V, is going to oppose this 6.5454. So that's going to be V. Our sign convention was if the left side's going up, the right side's going down, that is positive. So this is going to be a plus shear, and whatever it takes to put in equilibrium, and it's this 6.5454. Okay. So shear is pretty easy, just some forces in the Y. If there's only one force out there, then you just balance that one force. Moments, also easy. You just take a moment about your location. So moments about this 4-meter location, 6.5454 times 4 meters. $26,1816. Oops, 26,1816, and that's going to be kilonewton meters, right? So that external moment is going this way. So then my internal moment is going to go that way. All right, and when we get to kind of thinking about deflection, we're going to think about what's called end effect. So the end effect of this little section is concave up. Did you look up convex? Is it? So concave is where it's tilted up? Like ends are rotating up? Yeah, convex. Okay, cool. So this one, right, the end effects are like this. That's a positive moment. I think of smiley face, frowny face, but whatever works for you. If those ends rotate up, that's a positive moment. If those ends rotate down, that's a negative moment. So kind of another little moment convention for the internal moment. So then you do the same thing at what they want, 7 meters. Yeah, so another little section at 7 meters. Comes all the way over. It picks up the 12 this time. We still have the 6.5454. That is 5 meters. So this is 2 meters. Nothing else, right? No other forces. The X is still 0. So you draw that little section. Again, I like to put a little cut in there. And then you just do the same thing, right? Some forces in the Y. So now the 12 shows up. So we're left over with 5.4546, and that's coming down. So my V force would have to balance that and go up. Okay, so summing forces out on the beam and then balance it with this V force. So the effect out here on the beam is a down effect, right? Because we got 12 coming down, 6 going up. So the effect out here is down. The V force is up. That is a negative shear force. So this would be negative. This positive. Beam effect here going up. That's kind of what we did in class, and then I kind of just briefly introduced diagrams. So I want to confirm our answer at the 4 and the 7 with a diagram. So this is where we want to head to. We want to get to where we're drawing these diagrams. and then using maximums, right? So this is kind of just this is a good technique if you are not sure what the graph is doing. Is the graph going up and to the right, or is the graph going down to the left, or is the graph not linear, it's curved? If you just don't know, like you can't figure it out, you can plot points, right? This is a method of plotting points on the graph. So if you do it at 2 meters and you do it at 4 meters, it'll tell you where those points are, whether they're linear or not, whether they're nonlinear, parabolic, whatever they are. So if you're ever unsure, you can always use this technique to plot points. All right, so the diagram that we did before is just following the forces. So this is the shear diagram, and this is the zero line, and this force is going up 6.5454. So that's what I do, is I come up to that value. So that value, 6.5454. Okay, this was not part of this homework problem. I'm just doing it because this is where we're heading. Nothing changes, so that is horizontal line until you come to something. So now we come to the 12. So we have to drop 12. I went a little too far. Right? So it goes from 6.5454 and it drops down to 5.4545. And then nothing changes because there's no forces in this 6 meters. And then it should return. On all simple beams, it should return to 0. That's how you know you have a good diagram. Okay, so that's telling me that anywhere in this region, in this 6 meter region, is 5.4545, which is what we confirmed. And also it's negative. We can see that it's down below the 0 line. This is all negative, 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 negative. This is all positive, 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 right? So 6.5454 is all throughout this region. So we did it at 4 meters, but if you did it at 3 or 2 or 1, it's the same. So the graph is much more handy than trying to do individual locations. Unless you don't know what that graph's doing, and then it gets a little more complicated. Questions on that? It's pretty simple so far. The moment diagram we build from the shear diagram, okay? And the moment diagram is always a little trickier. You have to kind of know the progression of these graphs. Horizontal straight line is going to turn into a sloped straight line. A sloped straight line would turn into a parabolic curve. So that's the progression we got to remember. Horizontal to inclined straight line, linear, to parabolic. So the only way you get to parabolic is if you have some kind of a load up here that creates a straight line graph in the shear, which that's going to be a distribution. We'll do some of those. When you have a distribution, it's going to create a straight line graph in the shear, which is going to create a parabolic curve in the moment. Okay. So we know that this is going to produce a straight line incline because it's positive. So positive means slope up and to the right. So that means my moment's going to do something like this throughout this region. It's going to do that. Then it's going to go negative, which is down and to the right. And for all simple beams, it's going to return to 0. Simple beams are beams that do not have a fixed support. They're either a knife edge or a roller or a pin, right? And they're at the ends. That's the simplest simple beam. So this becomes the moment diagram. So what we haven't talked about is how do we get this value? Because that's the value we want. That's M max, right? Because when we go to bending stress, we're going to need to know M max. You get the moment from the area of the shear curve. So the shear graph gives us the moment, the magnitude of the moment. So that means here, the moment here is the area to the left of the shear. Now, if the shear went up and down, had positive and negative, then you'd have to take positive and negative and add them together, keeping their negative and positive, right? That's going to counter each other. But this is all just positive, and it's the area of this that gives us that number. If we wanted the value here, it would be the area to the left of this, where we'd take a plus and then a portion of this negative and subtract it from it. So area of a rectangle is about the easiest darn thing, right? 5 meters and 6.5454. That's going to give it, and this is kilonewtons. That'll give us the moment here, the max moment. 5 times 6.5454, 32,727, right here. M max 32.727 kilonewton meters. Because it is a moment, kilonewton meters, and we multiplied meters times kilonewtons. Okay? So we can check this because we did calculate the moment at 4 meters, right? We did that with our little section. So according to our graph, what would the moment be at 4 meters? It would be 4 times 6.5454, and you can see that's what we did here. It's exactly the same. We could check it at 7. We'd have to do this area minus this area, and we would get whatever moment we came up with here. Looks like I didn't write it down, right? So it is just the area of the shear that gives you that maximum moment. And that's, we just need max. Like if we're doing a beam and we're trying to decide if this thing's good or not good, we need to find the max moment and then calculate the bending stress, which we'll get to. All right, let's do the second one. Unless you have any questions on that. See what the second one produces. Check my reactions, make sure I didn't muck those up. I got 11.11 and 18.88. Oh, good. For these reactions. Okay. So again, this thing's asking us for the moment at 4 meters and 7 meters. I'm going to draw, and the shear. I'm going to draw the two diagrams to figure it out. You've already done the sections. If you did the homework, you've done the sections. So you have your number, and we'll see what my number produces. So the shear diagram is going to start with what? Going up. Yeah. 11.11. And then what happens for 3 meters? Nothing, stays the same. Hits the 10 and then goes to, yep, just be careful with that. And I always kind of exaggerate it. I don't get it too close to horizontal. I don't want to screw that up. But this now is 1.11. Then it comes across, nothing changes until it hits the 20. Then it goes down quite a bit. Scale's not perfect. $18.89. $8.87. That one says 8.8. Nothing happens, and then it should return to 0. Cool. Yeah.
So when you're labeling that, the 11.1, really the 1.11,
Uh-huh.
do you want us to label that or do we label the change?
Up to you how you do it. You just need to be able to calculate areas easily, right? So I label it here because I know I'm going to use a little portion of this rectangle here in the positive side to calculate what I need at 4. So the first one they wanted was at 4 meters. That's in here somewhere, right? So I'm going to need to know what that little area is. So that 1.11 becomes handy for it. you know the change is that, right? It's the 10. So it's already kind of written down. I don't know. However, whatever works for you, for sure. Yeah. So the shear at 4 meters would be this area, right? Where I have 3 times 11, 11. So that's the big rectangle here is 33.33. And then I have 1.11 times another 1 meter. So I get 34.44. So V at 4 meters is 34.44 kilonewtons. Is that what you got with your section? Perfect. So this is V, this is shear. So the first diagram is your shear diagram. And that's going to be in kilonewtons. Oh, sorry. Yeah, that is M. Sorry. I am way thinking ahead here. Sorry. You just read the graph to get the shear. So the shear at 4 is 1.11 kilonewtons. That should be what you got. I was already going for the moment. Yeah, so when we're doing the shear, you just read the graph, whatever it is. The shear at 7 is going to be right here, right? And it goes from 1.11 to 18.887 at that location. So you'd always use that bigger 18.887. That should be what you got. It would be negative, absolutely. I shouldn't have scratched out too far because I'm going to use it down here. So then the moment, I'm going to draw the graph just to practice. So this is what we do with, so this is positive, right? So what I call this is big positive. So this is big positive slope, at least bigger than this. This is a little positive slope. And I always kind of over dramatize it when I draw it. So I might do something like that kind of steepness, and then this kind of steepness, right? They're still both positive, but one's more positive than the other, if that makes sense on the slope scale. So this coming right through my numbers over to here, right? And then it goes negative. And it has a pretty big negative slope to it, so it's pretty steep coming back. So that black line is the moment curve, right? You just follow that slope, plus to a little bit of plus to a bunch of negative slope. And again, to get a specific spot, it's just the area of the shear diagram. So to get it at 4 meters, that's right here. We just did it up here, but it's that area plus this little area. So if I wrote it out, moment at 4 meters, it would be 11.11 times its rectangular distance on the base, which is 3 meters, plus 1.11 times 1 meter. So that's the areas. So it's going to be, the big rectangle stops here at 3 meters, right? So this 1111 is times 3. And then we got to add to it this little rectangle, which is 1.11 times 1 meter. And that gave us 34.44 kilonewton meters. And it's positive. This entire moment curve is positive, all up here. Which means the entire beam is deflecting with concavity, right? It's concave. All right, then at 7 meters, we got to do this again. So at 7 meters, we have a moment at 7 meters equal to, again, I need this rectangle, 11.11 times 3 meters. I'm going to add to it the entire little piece, 1.11 times 4 meters. So this area plus this area gives it to me at 7 meters, which is right here, 3 and the 4. What'd you get? Yep. And again, it's positive. Concavity, those ends are turned up. Same with this one, those ends are turned up. Both plus. When the ends are turned down, that's negative. No, book wanted you to do it with your sections. This is the way we're gonna do it now that we're past that. Yep. This is definitely the way to do it. And here's where I'm talking about this graph. If you're just not sure what the graph was doing, you could plot those points just like you did with a section. And you could plot like here, here, and here and go, oh, that's a linear growth. That's a straight line. Or that's not a linear growth. That must be some kind of curve up or curve down. So the curve up and curve down, whether the parabolic curve goes like this or the parabolic curve goes like this, right? That's going down. And this is also going down, but those are two different curves. So we know what's happening based on the slope of the shear, but it gets kind of weird when you get an angle in the shear. It's like positive slope, but decreasing positive, or it's positive slope, but it's increasing positive. So that's, this is maybe negative slope and decreasing negative. And this is negative slope, but increasing negative. Anyway, it gets kind of weird, but with a little practice, I think you'll get it on the kind of tougher ones. All right, let's do the next ones. 12, I think, said draw the shear. Is that right? Yeah. Draw the complete shear diagram. Yep. So check me on my reactions. I got 19.83 and 11.166. All right, I'm 3 for 3. Pretty happy about that. All right, follow the graph, right? Follow the forces for the graph, for the shear graph. I'm going to come up to 19.83. And that is Kips, because shear is force. And then we move along until something changes. And now we have 13 going down. Follow that down, takes us down to what? 6.83. Don't recommend doing it in your head. Nothing changes. Drops a total of 18. So that's going to be somewhere in the 12 or 11-ish. So that 3 repeats. $11.166. Into the negative region. And if everything's worked out it sees this last force and returns. So if they're saying draw the full shear, that's what they're looking for. That's what I'm looking for, is the full diagram with the major points labeled. That's it. So now the maximum shear on this beam would be what? What number? Biggest number you see. Absolute value of the biggest number you see, 19.83. And that maximum shear occurs over the first 2 foot region of the beam. Everywhere in that first 2 feet, it feels it. Good. All right, so then the moment we would think about slope, big plus, little plus, fairly big negative, right? So again, it goes up. I'm going to take it up pretty steep. And when you're doing this, you're just guessing at scale, right? Just think about, oh, okay, it's steep here, but it's less steep. It's still up, but it is less up until there, and then it is down. So all of that is good for drawing it. Really, all we care about are those major points. I know the problem didn't ask for it. I'm just doing it for practice. Okay. Where does the maximum moment occur? At the 18,000 force. Yep. So here's another little rule for the moment. The maximum will always occur where the shear crosses 0. So where the shear crosses 0 right here, that will be a maximum or a minimum. It could be down here, but it will be a max or min. Now the shear can cross 0 multiple times on a complicated beam, but that just means, hey, there's maximums and minimums at that location. It won't all be the same value, so there'll be some other, single number that's the biggest, but that just means it goes up and down a lot, is what that means. And if we wanted that moment, it would be that area plus that area to get our maximum moment. Yeah, good. Really cool. All right, let's do another one. I'm not going to calculate it. I just want to draw them. So I can give you this diagram with no numbers, and you can draw the moment diagram just by looking at it, right? Because you just got to follow the slope. You couldn't label any points, but. All right, let's do this one. Shear diagram. What's it do in the beginning? Goes up 16. Then what? Stays constant, nothing changes. Wow, left off my arrowheads. That was bugging me. Then it drops, how much? 10 to 6K. Then nothing changes. And then it drops a total of 12. So it drops down to minus 6K. Then nothing changes. And about this time, you should be like, oh, I see symmetry. So pretty much know what this thing does. Right, so this is gonna be 16K. Good. Fairly easy. Concentrated loads, even if they go up and down, it's pretty straightforward drawing the shear. Distributions are a little more challenging to figure out, but no big deal. The moment, what would it look like? It's going to go plus to a little minus to more minus, right? So I know plus slope is like this. And then less plus slope would be like this. And then some little negative slope. And actually that would come across to about the same spot, right? So we have symmetry. and then come down to 0. It looks something like that. We know maximum moment occurs where the shear crosses 0. So boom, that's right there, maximum moment there. If I wanted the value, calculate the area to the left. It'll give it to you. Cool. All right. Turn those in if you got them. Yep. And I have one more prepped up for us. Because really, we just need a lot of practice at these, and we need to get a little more complicated with them. So I have a cantilever beam, has a fixed support and then a free end. It is 14B if you want to look at it in your book. But I have everything on screen except for the distances. I need those. 14B is kind of above the 14. Whoops. It's actually 15B. Did I write 14B? It's 15B. And I need some distances. It's like it's 4 feet, 6 feet, and 8 feet. So 4 feet. And then from here to here is 6 feet. And then from here to here is 8 feet. Has a distribution on it. And it has 2 concentrated. So I'll give you a second to write it down. (15B). All right, so I also added, maybe you noticed, I said, hey, this beam is 4x13 structural steel shape. It's A36 steel. So I'm going to take it all the way out and say, figure out whether this is good or bad, right? We can actually run a little bending stress when we're done. But what do we do first when we're given a problem like this? Step 1 is, overthink it. Perfect. Find the reactions. Yeah, so statics is step 1. So now we have to like, oh, what reactions are there in a fixed? Yep, X, Y. I'm going to guess Y goes up. I'll call it AY, AX, and a moment at A. Notice I put my moment in opposing what I think is going to be the beam moment, right? Looks like the beam moment is going to be down and around, right? So yeah, those are the 3. AX is equal to 0, nothing going on in the X. AY is equal to, like in layman's words, what's AY equal to? Yeah, all the forces going down out there. So we just got to calculate all the forces going down. We got 12 down, 2 down, and 1 kip per foot over the 6 and 8 region, right? So over the 14 feet. So 12 and 2 and 14 times 1 is 14. 28 coming down? Yeah. AY equals 28K going up to oppose the 28 coming down. What about the moment? We just got to calculate the moment, right? At this location over here at A. So that's going to be 12 times its distance, 2 times its distance. And then how do we do a distribution? Concentrated, yep. Concentrated at its geometric center. So we only do that for the statics part. Then we want the distribution back. So for the statics part, we're going to use 1 times 14, that's 14K, and we're going to put it halfway, right? And half of the 14 is going to be 7. So this is the concentration of the distribution. We need it for the statics part. We are not going to use it for the strengths part. We're going to go back to the distribution. All right, so that moment at A, I'm going to write up above. I'm going to go 12K times, how long is this thing? 18 feet? 18 feet, and that looks like it's going to be a positive moment, right? Counterclockwise. And then I'm going to put the 2 in. Also a positive moment times 8 feet. So there's the 2 concentrations. Then I'm going to put the 14 in. That's my concentrated distribution times its lever arm of 7 feet. Super kind of important that we get that right, or our strengths part is trash. So if we muck up the statics, we don't have a fighting chance on the strengths. $330? What are the units of that? Yeah, I'm gonna write kip feet, but it's fine either way. Foot kips, kip feet. All right, statics is done. All right, good. Now what? Diagrams, absolutely. What does the diagram do? It's gonna get weird. It goes down, right? And my scale is going to be really small because I know this is going to head like way down. So it goes down to what? Yep, minus 12K. And then for 4 feet, nothing. Then what happens? Yeah, so it's going to head down, but it's not going to be horizontal. It increases, right? For every foot, it goes down what? 1 kip, right? So at 1 foot, it goes like this. And then at 2 foot, it goes down another and another and another. It's linear, dropping the same amount every time. So a horizontal distribution creates a sloped straight line. That's the progression that we talked about before, but this just proves it. And my slope is probably way too steep, so I'm going to back that off a little bit. And I'm going to carry it until something changes, right? I'm going to carry it to the 2K. And then what happens? We have a shear spike of 2K. Again, I'll exaggerate that a little bit. My scale's off. Seldom drawn to scale anyway. But I need to know what this number is before I apply the 2K, right? So how far did I come over with my distribution? So it dropped a total of 6 kip in the 6 feet, right? So this number is what? 18. And then this number is 20. We are using the distribution now. So this concentration is gone. We only use that concentration for the statics part, but now we're into the strengths part and we're using the distribution. All right. And then it continues on at that same slope over a region of 8 feet. So that means it drops another 8 during this slope. So I always match my slopes because this slope and this new slope should be the same, right? Because they're the same distribution. So it dropped a total of 8. So this should be down to 28. And if everything's good, if you've done everything right, then that reaction brings it back to 0. So the shear does return to 0. The moment will not return to 0 because we have a hanging out moment over here, actually a big hanging out moment, MA of 330 kip feet. So it's definitely not going to go to 0 at a fixed. It's going to be like maximized. All right. So now we know we can build this moment diagram from the shear diagram, as long as I have all the information. So I'm going to just put down some information. 4 feet. And then this is another 6 feet. And then this is 8 feet. Yeah, go for it, Kyle. You can check the recording. Kyle is leaving now. There, you can look for that marker. It's not a thing. Yep. All right, so we're minus slope, right? And then we're like minus, but getting more minus. And then we're minus and getting bigger minus. So this is a negative slope, uniform. This is a negative slope getting more negative. So that's non-uniform. And this is also negative slope and getting more negative as it goes. So it's going from, I got to do this correctly. It's going from negative and getting more negative as it progresses. Does that make sense? So that is going to, yep. Yeah, so these little spikes, when I like to put little blips in the curve because the curve would have a little micro blip in it, but that's pretty hard to draw. But these are called moment spikes. So it's nice to bring your curve and then like have it change slope kind of immediately just to clarify. But you see it here. You always use 2 graphs together. So yeah. All right, so let's draw this thing. This is going to be negative slope. And we know it starts at 0. Right? Because at the very end of a cantilever, there's no moment out there. So it starts at 0 and it goes to here. That was probably way too steep. I'm going to pay for that in my graph, but I'm going to stick with it because I did it in pen. Then it goes from there and it gets, so this is how I do it. This is my technique. You can adopt it if you want. It works good for me. I put little markers in. Okay, right here it is essentially the same slope, right? And then here it gets more slopey. And then here it gets even more slopey, right? So that gives me the kind of graph that it is. It does something like that. In other words, it's negative and getting bigger negative. And it's that 2nd degree parabola. And then there's a little spike of some kind. I would just put a dot probably. And then it continues on that same kind of slope. Yeah, well, that's because I started so steep here. I should have started really flat and then it wouldn't be so dramatic, but that's all right. And it ends here, right? So then to get that moment, clearly the maximum moment is right here. I would need this entire area. Yeah. So this area is not that fun to calculate. But we also know that, hey, wait a second, we already calculated the moment here, right? And it looks like that is the maximum moment. And for a cantilever, the maximum moment is always at the fixed point, for sure. If I wanted it somewhere else, I could get it. I'd have to go up here and do a little triangle area stuff and rectangles and just add them all together. But really what I want is that, the max, and that is the max, 330.
So something like this.
Yep.
is this complicated, it almost seems easier to do what we did above
Yep.
instead of breaking that crazy deep.
Yeah, absolutely. I wouldn't go for this area unless I was just trying to confirm my number. Like, hey, I need to make sure that number's right. So then I could just crunch the, I mean, it's not that fun, but it's really not that difficult, right? It's a triangle, a rectangle, a triangle, and then a rectangle. Wouldn't be that hard to just crunch that out. That's how I do it. I wouldn't go to trapezoids or whatever they're called. But that would be the only reason. It gets a little more complicated when you throw a support in here, like a cantilever support. Then this graph is going to do all kinds of things like this. Right? And so then, oh, I got to find out what that is. I got to find out what that is and see which one's bigger because I can't trust my graph because I never draw it to a great scale. So then you got to go up and do some areas at some certain locations. So yeah, sometimes it's just flat out easier to say, okay, I know there's a max here, go section the beam and take a moment up there. So then I don't even have to deal with the areas of the shear because the shear can be parabolic and that's just a pain. Like I really don't want to integrate over a curve. It's been too long, right? So yeah, it's easier to go, oh, just go section the beam and do moments up there. It'll tell me what it is. All right, good job. You have some more of these to do.
So then we could compare that moment with,
That one you could compare to adding up these areas. Should be exactly the same. Yeah, so oh, thank you. I was going to take it all the way out, wasn't I? So then, wait, it won't take that long. Once you determine max moment, that's it right there, 330. Then we can say, okay, what's the maximum bending stress? Bending stress is MC over I. M is the max moment. So that's what we just calculated at 330. Kip feet. Units are super important. C, so an I shape is this, right? So C is the distance from the neutral axis to the outermost fiber. So I just need to know what the true height of this 4 inches. Probably not 4 inches, so we look that up. Might be 4 inches on a little guy like that. 4 by 13 is, oh yeah, 4.16 in height. So C is going to be 4.16 divided by 2. .08 inches. Super important. We got to watch these units. And then I for a W shape, we look up. So yeah, that's the area moment of inertia. Exactly. 4 by 13. And we want IX because this thing's loaded against the x-axis perpendicular to it. So what's our IX value? 11.3 inches to the 4th. So we have a kip foot inches and inches to the fourth, we need to get this kip foot to kip inches. So we can get a unit of kips per inches squared. So I know there's 12 inches in 1 foot. So that's a unit analysis thing, right? Because now I can do what with the feet? Cross them off. So my bending stress is going to be 330 kips times 2.08 times 12 divided by 11.3. Anyone get a number? 728.92. And what are the units? KSI. And what is the yield of A36 steel? 36 is the Q, that's the clue. A36 is 36,000 PSI yield. PSI. We have what? We have 728,000 PSI. This thing failed days ago, like long time ago. This thing could never carry 12,000 pounds out here at the end. It would miserably fail. Yeah, it's a 4-inch little W shape. Yep.
With the fixed portion at the end,
Yep.
how would you calculate, how would you factor that in? Are you just accounting for the beam? Say it's one.
So yeah, this is just the analysis of the beam, not the connection. Yeah. So the connection, the way you would do if it was like welded to something, like there's a weldment there, that weldment would have to withstand 28,000 pounds of shear. That's how that weldment would probably fail. Potentially you could rip it off with the moment, but that's a much harder calculation. Yeah. So what you have to do is you have to say, okay, 28,000 pounds over the weldment area. So what size weldment did we use? 1/4 inch, 3/8, 1/2 inch, whatever we used, and how much weldment area is there? Yep. Yep. So you calculate all that out and determine your area, your shear area. And then it's just P over A.
Which
It's
would be that 12.
with that, if that's all you did, yeah, absolutely.
Would you take into account how far it penetrated into the?
Well, you should. The assumption when you do the math as an engineer, the assumption is that's a certified weld and the penetration is good, like 100% penetration. It's a big assumption, but that's why in structural systems, we use certified welders. Like you can't be, Joe Farm Boy and weld for me if I'm going to put something to work and put it out in public, right? You need certified weldments. And then if you have a system that's going to go out and potentially be used by the public, then there's testing on the weldments as you go through the process. So,
Is there a factor?
oh, absolutely. Freaking giant one. Yeah. Yeah, the homework is I'm going to tell you, I don't remember.